Now let's go to some questions. Did we discuss these questions? Just let me know. Exercise 8, question 14. No. 15. No. So let's start with exercise 8. Question 14, 15. Did we do 13? No. Yeah. Start with exercise 8, question 13, 14, and 15. Exercise 8, question 13, 14, and 15. Start with these three questions. Exercise 8, question 13, 14, and 15. Question 13, 14, and 15. I'll give some time for that. Well, so, like, you need to get the past paper tute. And do you have that extra tute we gave other than the main tute? Yes? Yes, everyone? Yes? No? Others? Yes, right? Okay. I asked you to do exercise 8, question 13, 14, and 15. Question 13, 14, and 15, exercise 8. Okay, tutes will be provided in the Zoom chat now. Okay, tutes will be provided in the Zoom chat now, and give us like 2 minutes. Tutes will be provided in the Zoom chat. And other than that, like you can get the tutes delivered. Okay, I'll tell you how you can get the tutes delivered. Asked you to try exercise 8, question 13, 14, and 15. If you can't do the question, at least revise the content. Any physical students who don't have the main book? No, right? Okay. Main tute is provided in the Zoom chat. There you have to try exercise 8, question 13, 14, and 15. And if you don't have the, like, if you need to get the tutes delivered, send a message to this number with all your information, not 70-154-6825. Not 70-154-6825. Send a message to this number with your information. They'll request your information with the tutes. They'll request your information, give the information, then they'll send you the tutes. Single. Then, like, if I like quickly go through the content a bit, the idea was two parallel capacitors, two or three of you parallel capacitors, C1, C2. You get the resultant as C1 plus C2. You get the resultant as C1 plus C2. Few series capacitors, C1, C2, you will get 1 over C equals 1 over C1 plus 1 over C2. Using this, you will get the resultant. 1 over C equals 1 over C1 plus 1 over C2. Using this, you will get the resultant. Then after this, the same series parallel configuration we saw, uh, like this. You just fill the capacitor, by two different materials. You just fill the capacitor by two different materials. Now this is actually series, okay? This is actually series. Then you can fill the capacitor by two materials like this as K1 and K2. Uh, then this is actually a parallel capacitor. This is actually a parallel capacitor. Okay. It's actually a parallel capacitor. Okay. So like that we started doing calculations. Okay. We did calculations for these. Then uh, after that, we checked what happens when we put a conductor into this. Uh, We checked what happens when we put a conductor into this. That means if you have a whole like capacitor, if the length is d, if this is b, if this is b, if the area is a, the capacitors we got as a epsilon d minus b. What happened was we just have to remove the length b from the total length d. Okay, that's all. That's how we started the lesson. Okay, that's where we stopped. So go to question 13, 14, and 15, exercise 8. Okay, I'll start with question 13. I'll start with question 13. In question 13, what they mention is, I explained you, like, one thing to understand is in question 13, the plates are like this, right? Sorry, before that, I'll start from question 15. Do you start working with question 13? Yes, right? Okay, then I'll go with 13. In question 13, you had a 2 microfarad capacitor and a 3 microfarad capacitor, right? You had a 2 microfarad capacitor and a 3 microfarad capacitor. This is not actually from last week content, it's the week before that, right? As I remember. So you have a 2 microfarad capacitor and a 3 microfarad capacitor. You give a total voltage difference of 50 volt to this, okay? You give a total voltage difference of 50 volt to this. Then the question is, after that, after giving these 50 volts, we isolate these two capacitors. We isolate these two capacitors and connect them parallel to each other, right? We isolate these capacitors and connect them parallel to each other. Clear? Connect them parallel to each other. Clear? That means we know when we connect something in series, it will look like plus Q minus Q, plus Q minus Q, like this, right? It will look like this, right? Plus Q minus Q plus Q minus Q, right? This is the configuration that happens when we put them in series, right? Configuration of chargers, clear? Uh, so the first thing is finding Q, right? First step is finding Q. So when finding Q, you have this option, okay? If you like, you have this option. You know that there's a equivalent capacitors to this, right? You know that there's a equivalent capacitor to this, okay? And the whole story of equivalent capacitor, whole idea of equivalent capacitor is if this one gets Q when given 50 volts, this one should get Q too, okay? That's the whole idea of equivalent capacitor, right? That's the whole idea of equivalent capacitor, clear? If when we give 50 volts, if this one gets Q, this one must get Q, clear? Clear? That's the whole idea of the equivalent capacitor. So it's easy to find Q using the equivalent capacitor, right? It's easy to find Q using the equivalent capacitor, right? Clear? That means this is a 2 microfarad capacitor and a 3 microfarad capacitor. How can I get the equivalent? 1 over C equals 1 over 2 plus 1 over 3. So C equals 2 into 3 over 2 plus 3, which means 6 over 5. Clear? Which means 6 over 5 microfarad. Clear? 6 over 5 microfarad. Clear? We get 6 over 5 microfarad. So that is the capacitance. Clear? That is the capacitance. Okay. So here we apply Q equals CV. We apply Q equals CV. Charge is Q. Capacitance is 6 over 5 micro. 6 over 5 micro. Voltage 50 volt. Voltage 50 volt, which gives the overall of 60 microcoulomb, right? I again convert 10 into 10 to the power minus 6 into micro. So you get an overall of 60 microcoulomb, right? So here it's only 60 microcoulomb. Here, this one gets 60, this one gets 60, right? Here in the series configuration, this one gets 60 and this one gets 60, clear? So now what happens is you have two capacitors. You have two capacitors. One have plus 60 and minus 60. Other one have again plus 60 and minus 60. You connect them like this. You connect them like this. Clear? Ah. So when you connect them like that, what happens? When you connect them like that, what happens? When you connect them like that, they should turn into a common potential. When you connect them like this, they should turn into a common potential. That means when you connect two capacitors like this, if one capacitor has a higher potential and the other capacitor has a lower potential, charge flows from the higher potential capacitor to lower potential capacitor until the potential values become equal, right? Until the potential values become equal. So they will exchange charge until they are in a common potential value. Clear? Until they are in a common potential value. And this is a 2 microfarad capacitor. This is a 3 microfarad capacitor. Clear? Ah. So how can I do the calculations now? Don't think about a moving charge. Overall, you have 160 microcoulombs in this side, right? Overall, you have 120. Sorry, 60 plus 60, 120. Overall, you have 120 microcoulombs in this side, right? This 120 should be distributed between these two plates accordingly, such that they have the same potential. Clear? So if this one gets Q, this one should get 120 minus Q. Clear? This side should get 120 minus Q. Clear? Then in this side also same thing happens. Okay. This minus 120, this minus 120 will be distributed accordingly. Clear? This minus 120 will be distributed accordingly. Clear? They should be distributed accordingly. Okay. So the next thing. So now, what is the equation for V potential? Q equals CV. V equals Q over C. So for this one, I can write the potential. This one, I can write the potential as Q. What is the charge? Q, simple Q. Simple Q over, what is the capacitance? Capacitance is 2, clear? Capacitance is 2. Then for the other one, I can write, for the other one, it is 120 minus simple Q, right? For the other one, it is 120 minus simple Q. It is 120 minus simple Q. Here, it is 3. Here, it is 3. Here, it is 3. Clear? 120 minus Q over 3. Clear? So you get cross multiply 3Q equals 240 minus 2Q. 5Q equals 240. Q equals 240 divided by 5. What do we get when we divide 240 by 5? 48, right? 48, right? Yes, right? Yeah. So you get 48 microcoulomb. You have 48 microcoulomb in this capacitor, and in the other capacitor, you have 120 minus Q. That means 120 minus 48 microcoulomb. 120 minus 48 microcoulomb. Then if you need to find the common potential, you can write Q over 2. You can write Q over 2. Q over 2. Apply Q over 2 to anyone. Why? Potentials are equal. Okay. So here, simple Q is 48 microcoulomb. 48 microcoulomb. Here you get 48 microcoulomb. Here you get, this is not just 2, it should be 2 microfarad. It's 2 microfarad. Okay. 2 microfarad. When you solve this, you get 24 volts. Clear? You get 24 volts. Clear? You have 48 microcoulomb here. You divide it by 2 microfarad. Clear? You get overall of 24 volts. Clear? You get overall of 24 volts. Clear? Got the idea? Clear? You get overall of 24 volts. Write this down. I'll quickly move to question 14 next. Keep it here. Uh, okay, next one. Next one. Question 14, what they are telling is there's a conductor in between, right? There's a conductor in between, and it is initially, is this D or D over 2? D. Okay, it's initially D and D. Then we push the conductor a bit down, value of x. Then this length becomes D plus x. This length becomes D minus x, right? Clear? This length becomes D plus x. This length becomes D minus x, right? Clear? Clear? Ah. So the question is, then what is the potential difference between the upper plate and the center conductor, right? Next one is, what is the potential difference between the upper plate and the center conductor? Clear? The question is, what is V1? Clear? Question is, what is V1? we have given overall of V value, V potential to the whole capacitor. Clear? So the thing is, can you remember this conducting part is useless? Can you remember from last week's content? Conducting part will not have any field intensity inside that, right? Conducting part will not have any field intensity inside that. Clear? That means it just acts like this part has a separate capacitor and this part has a separate capacitor, right? You don't have to think about this center part. Clear? So an equivalent for this system would be you give a potential of V. Equivalent for this system would be this, right? This would be an equivalent for this system. Clear? This would be an equivalent for this system. So here, this capacitor I can consider as A epsilon naught d minus x. This I can get A epsilon naught d plus x. A epsilon naught d plus x. Clear? Why this gap is d plus x, this gap is d minus x. Clear? Clear? So this is C1. This is C1. This is C2. Clear? This is C1 and this is C2. So I need the potential of C1, which means V1. Clear? So I mean, for this question, there may be some easier methods to incorporate X and find answers. But I'll go with a conventional path which matches for any scenario, okay? So here, if the potential here is V1, potential here would be V2, right? Potential here would be V2, clear? And since they are series, if this is plus Q, this is minus Q, this is plus Q, this is minus Q, clear? Then I can apply Q equals CV. Then I can apply Q equals CV. Clear? Q equals CV. Okay. So I can write V1 equals Q over C1. V2 equals Q over C2, right? Then V equals Q over C. So V1 equals Q over C1. V2 equals Q over C2. Clear? So then V1 over V2 equals V1 over V2 equals Q over C1 over Q over C2. That means C2 over C1. Clear? C2 over C1. Clear? Then I have explained this before. For a ratio, if you do the same thing to both sides, still its equality holds, right? Clear? That means you can bring this V1 and add it here. V1 over, you bring this V1 and add it here. V1 plus V2. Clear? You bring this V1 and add it here. Clear? You do the same to this side. You bring this C2. You bring this C2 and add it here. You know that is possible, right? Clear? For a ratio, if you do the same thing to both sides, equality still holds. Clear? So the reason to do this is you have V1 now directly. Why? What is V1 plus V2? V1 plus V2 is V, right? See? V1 plus V2 is directly V, right? Clear? V1 plus V2 is directly V. Clear? So you have V1 over V. You have V1 over V. Clear? You have V1 over, what is V1 plus V2? It is V. Clear? Equals, here you have C2 plus C1. Then you get V1 equals C2 over C2 plus C1 into V. Now it's just substituting values. That means what is C2? C2 is A epsilon naught over D minus X. A epsilon naught over D minus X. Here you have again C2, A epsilon naught over D minus X. Again you have C1, which is A epsilon naught over, uh, what is C1? D plus X. C1 is A epsilon naught over D plus X. When I like solve this, when I try to solve this, I get A epsilon naught over D minus X. Here you get A epsilon naught D plus X plus D minus X over D minus X D plus X. Then D minus X and D minus X cancels out. D minus X and D minus X cancels out. Plus X and minus X cancels out. A epsilon naught cancels out. And you have here V2, okay? You have V2, V into V. Okay, here you have V. Then what happens? You get this D plus X goes up. You have D plus X. Here 2, here 2D, D plus X over here 2D into V. Into V. Clear? Got the idea? Ah, write this down. Let's go to 15. Okay, this one. Here the first thing is the plates are situated like this, okay? Plates are situated like this, right? Okay, that you should first figure out, okay? And here this is epsilon, the remaining part is epsilon naught, right? Clear? That's what they mentioned in the question, right? This is epsilon and the remaining part is epsilon naught. Clear? Ah, so I'll just turn it like this to make things easy. So now this is epsilon, the remaining part is epsilon naught. Remaining part is epsilon naught. Now again, we have two options. See, sometimes there's a tendency of drawing it like this. This is epsilon, this is epsilon naught, and this whole part is epsilon naught. This is wrong, right? Can you remember? This is not correct. This is not correct. Why? Can you remember the reason? See, the material is different here. So field here is different from the field here. Clear? So in this line, you won't have the same potential. Can you remember the theory from last week? In this line, you won't have the same potential. Clear? Clear? Because there's a different field here from here to here. There's a different field here from here to here. Clear? So you won't have the same potential in the line. Clear? You won't have the same potential in the line. Clear? Clear? You won't have the same potential. Got the idea? So if you don't have the same potential, okay, if you don't have the same potential, you can't draw a common plate here, right? Common plate means common potential, right? Common plate means common potential. So you can't have a common plate or common potential here, clear? You can't have a common plate or a common potential here, clear? Clear? Why? This line you can't guarantee a common potential, clear? So instead of that, you can get this whole part as epsilon naught, this part epsilon, this part epsilon naught. It's much convenient, right? It's much convenient, clear? It's much convenient because then that parallel issue doesn't appear, clear? That parallel issue doesn't appear, clear? So going with this one is correct. This is not reasonable. This is entirely wrong, okay? Clear? Clear? So let's move forward with this. Let's move forward with this. Uh, this is epsilon, this is epsilon naught. This is epsilon naught. So this is A epsilon over D. This is A epsilon naught over D. This is also A epsilon naught over D. Okay. Now you get the resultant, okay? Sorry. I should break down things, right? Do they give the total area as A and this as D? Yes, right? So then it should be here A over 2. Here A over 2. Here A over 2. And gap D over 2. Here gap D over 2. Here A over 2. Only A over 2. Clear? I'll write them again. This is area A over 2. Why? It is half of the area. Half of the total area. So A over 2 epsilon over D over 2. Here it is A over 2. This is epsilon. This is epsilon naught over D over 2. This is A over 2 epsilon naught over D. D. Clear? Clear? Now you can get the resultant. Clear? I'll take this one as C1, this one as C2, this one as C3. Then these two are series. These two are series. So 1 over C equals 1 over C1 plus 1 over C2, which gives you C equals C1 C2 over C1 plus C2. Then here you have C3. So this set and this set is parallel. So the overall is this one plus C3. This one plus C3. Clear? This bunch plus C3. Clear? Which gives you C1 C2 over C1 plus C2 plus C3. So substitute this one at C3. C1 is this one. C2 is this one and go for the answers. Okay, I'm not going to do the final calculations. Clear? Be careful. This is epsilon naught. This is epsilon naught. This is only epsilon. Clear? Clear? Be careful about that. Okay. Write this down. Write this down. Then you can find the past paper tubes, right? Well, we gave the past paper tubes in the Zoom chat, right? You'll be able to find the past paper tubes. Go to 2001 question first. 2005. We have only very small theory part remaining. It would take only 5 minutes, okay? There's a very small theory part remaining. It will take only 5 minutes. So yeah, officially done with the static electricity lesson. But I'm still thinking about the next week's plan. Whether we'll be moving to magnetics, whether we should move to a different lesson. Okay. I'm still thinking about that. What should be the ideal plan? Okay. What should be the ideal plan? But we'll see. Sometimes I may go to the next lesson magnetics, or I may give you some questions to do from static electricity and discuss them, or else I have the option of using this time and do heat for total 5 hours 6 hours and try to finish heat. Okay, we have very small part remaining in the heat lesson too. So if we can get all 6 hours next week for heat, we are done with the heat lesson too, then we can peacefully start magnetics lesson the week after that with current electricity lesson parallelly. Okay, so sometimes I may do use the next whole day for heat, which will be much convenient. So we'll think about that. Online students, let us know if you can't find a tute, okay? Online students, let us know if you can't find a tute. I need you go to the past paper tute, try 2001 question, then 2005 question. So we don't have a very specific plan for today after this, okay? We can move forward peacefully. So if you have any questions regarding any part, just ask, okay? Today we are just winding up the lesson. And we'll finish whatever the past papers we can finish, and the remaining questions I'll provide as a recording, okay? Just like we did for waves and optics. Hope you have watched the waves past paper recording and the optics past paper recording, okay? Don't like skip stuff, okay? And I mentioned this in the Sunday class too. For the upcoming months, okay? Whenever I find a time, I'll try to. I mean, I can't find a time. That is a different story. But whenever it's possible, I'll try to find a time and do some extra classes and finish the syllabus. Okay? Why? Because for the next 3 months, you're only going school for like 10 days. Okay? You have like now starting 1 week school, then after that Christmas holidays, then 5 days schools. After that, again holidays for A levels. Again like 5 6 days school or 10 days school. After that, holidays for O levels. Okay. So this is one of the best times that you can use effectively. Okay. So don't tell me that you don't have enough time. I'm doing many extra classes. Okay. Don't tell that thing. Okay. You have more than enough time. After that, after these 3 months, there's a minimum number of school days that should be there before A levels. There are some regulations like that. So you would get minimum holidays. Okay, after that you would get minimum holidays. So these 3 months we should use effectively. Okay, yes, if you are not going to school anyways, you don't have to think about this. Okay, so but for the people who go to the school for attendance or anything, after that you will have minimum holidays. Okay, so this is the time that you should use that we should use for this. Okay, this is the time that we should use to finish the syllabus. Okay, so whenever possible I'll try to come up with some extra classes and to do some extra sessions and try to finish the syllabus within next 2 months quickly. Okay, then it's done. Then again when the school starts, one subject is over. Okay, okay, then it's quite peaceful. Okay, it's quite peaceful because this is the largest syllabus. Okay, okay, this has the toughest syllabus in the all three subjects. Okay, so when when the school starts again, one subject is over. Okay, that should be our plan. Okay, go to 2001 question and 2005 question. So there will be recordings for some practicals. I'll give recordings. To finish theory, I'll put some online sessions or physical sessions. Like that, there will be recordings, online sessions, physical sessions, mix of things. If it was school days, I know it's quite hectic. Okay, why you have to go to school, then there's a recording, then there's online class, then again there's the physical class, there's a lot of work. But these days, it's not like that. You have more than enough holidays. Okay, you have more than enough holidays. So don't like expect me to go slow these days. Okay, I'll accelerate these days. I'll use recordings sometimes, I'll use online classes sometimes, I'll use physical classes sometimes, and I'll somehow finish things within 2 months. Okay, that is my main plan at the moment. And if you have any questions, ask. Okay. If you have any questions, ask. I'll give time for each past paper, and we'll keep doing past papers today. And there's a 5 minute theory part also. It's not a very difficult question, okay? 2001 question. Directly theory, okay? It's a spherical shell system, right? Yes, right? It's directly theory. So, right, do right answers as fast as possible within the given time. Point charge plus 1 microcoulomb is placed at the center of an isolated conducting spherical shell of inner radius 10 centimeter, outer radius 15 centimeter as shown in the diagram. The point P, Q, R, S and T shown in the diagram. What is the induced charge on the inner? Okay. I'm not going to do the question in order. Hope you have at least read the whole question. Okay. I'm not going to go in the correct order. I'll just quickly write all the answers. Okay. Okay. And there's a specific reason to choose this question first. Okay. There's a small theory point that I need to teach. Okay. So you have plus 1 microcoulomb at the center. You have plus 1 microcoulomb at the center. Then you have a shell like this. Then you have a shell like this. So can you remember we had a like easy method for this, right? Can you remember? We had an easy method for this. We converted this into a thin shell system. Can you remember? How we tackle this question was different, right? We converted this into a thin shell system. Okay. But in this question, they are assuming that we don't know that method because they haven't asked us to teach that method, that short method I taught you. Okay. So they are assuming that we don't know that short method and they are taking us through a different path. So let's go through that path. Okay. They are taking us through a different path. Okay. What is that? First, find induced charges. What are the induced charges? If this is plus 1, in this surface, it becomes minus 1, right? Minus 1 gets induced. Then by this minus 1, another plus 1 gets induced, right? Okay, this is plus 1, this is minus 1, again plus 1. Okay, it continuously induce, clear? It continuously induce, clear? Plus 1, minus 1, plus 1, like this. Then they're asking us to find the field intensities here, here, and here, right? Clear? What is the field intensity here? When you are writing the field intensity here, you just get the whole bunch of charges and write a total here, right? Write a total here. So plus 1 minus 1 plus 1 results in plus 1. So you get 1 over 4 pi epsilon, 1 over 4 pi epsilon. Overall charge inside this is 1 microcoulomb. 1 microcoulomb. What is this distance? They are asking to find the field intensity at P. Distance to P from the center is 20 centimeters. Distance to the P from the center is 20 centimeters. So 20 into 10 to the power minus 2 squared. Then here, what is the field intensity? 0. Can you remember? Inside a conductor, there can't be a field intensity. Can you remember that theory point? Inside a conductor, there can't be a there can't be a charge. So there can't be what? There can't be a field. Okay. No charge exists inside a conductor. No charge exists inside a conductor. So as a result, there's no field intensity inside the conductor. Can you remember? Okay. Then here, when you write the field intensity here, what affects the field intensity here is only the charge inside this circle. Can you remember? So you can forget minus 1 and plus 1. Okay. So you write 1 over 4 pi epsilon. 1 over 4 pi epsilon. Charge 1 into 10 to the power minus 6 over distance. What is the distance to this point? They're asking the field intensity at T. What is T? OT is 5 centimeters. OT is 5 centimeters. Clear? Okay. Then they're asking us to find the potential, right? They're asking us to find the potential here, 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 and here, right? At 5 places, right? Writing the potential here is easy. Just 1 over 4 pi epsilon. You just consider the whole charge inside. Whole charge inside is plus 1 minus 1 plus 1, which results in plus 1. So 1 into 10 to the power minus 6 divided by the distance. What is the distance? 20 into, again, the distance is 20, right? 10 to the power minus not 2 squared, it's just 10 to the power minus 2. Clear? Then at the surface, equation doesn't change, right? At the surface, equation doesn't change. 1 over 4 pi epsilon, charge still 1 into 10 to the power minus 6. Only the distance is not 20. Now, what is the distance from the center to the point Q? OQ is 15 centimeters. OQ is 15 centimeters. Clear? Then, for the remaining 3 points, you have the same potential, right? Here you have the same potential. Here you have the same potential. Clear? Why? Conductor is an equipotential object or equipotential surface. So throughout the conductor, everywhere in a conductor, you have the same potential. Clear? Everywhere in a conductor, you have the same potential. Clear? Everywhere in a conductor, you have the same potential. Clear? Got the idea? So it's the same potential throughout the conductor. Got the idea? Okay. Now they need us to find the potential at a point like this. They need us to find the potential at a point like this. So initially, we had a better method for this. We convert this into a thin shell system. Using a thin shell system, we write potential values. Clear? We convert the system into a thin shell system. Then using the thin shell system, okay, we write the potential. Now they think that we don't know that method. So they guide through us a different method. So in question 3 part B, they mention us something like this. In question 3 part B, they mention us something like this. It is, they're asking us to first, before writing the potential here, I know the potential here, right? They're asking us to write the potential difference here, delta V. Okay. How can I write delta V? Writing delta V is easy. Why? From here to here, field intensity is created only by this guy, right? So it's easy to write the potential difference from here to here. How? 1 over 4 pi epsilon. Here internal charge is 1 into 10 to the power minus 6. What is the distance from the center to here? It is OS. OS is 10 centimeters. From the center to here, distance is 10 centimeters. 10 centimeters. Then they are asking us to find the value at T. What is the distance to T? T, it is 5 centimeters. 5 centimeters. So what I'm going to do is, here I'll put 10 centimeters. Here I'll put 5 centimeters. What is the meaning of this? What is the meaning of this? See what has happened here. You have 1 over 4 pi epsilon. This minus this. Clear? This is 1 over 4 pi epsilon. Charge is 1 micro. Here, when you write the potential here, you divide by 5 into 10 to the power minus 2. Distance to that point is 5 into 10 to the power minus 2. Minus, here, it is 10 into 10 to the power minus 2. This is not the actual potential here. This is not the actual potential here. This is just the difference of potential between these 2 points by this charge. Clear? This is not the actual potential here. This is not the actual potential here. This is just the potential difference by 1 microcoulomb. And one thing I know, that is this potential difference is created by only 1 microcoulomb. Why? Other charges are outside now. Clear? What affects the difference is this guy. Clear? So this is the difference between this and this. And then in the next step, they are asking us to use this to find the potential at T. How can I do that? I know the potential here. That was equal to the potential at the surface. So I know the potential at the surface, so I know the potential here, which is this. Then I know the potential difference from here to here. So potential here plus the difference, you get the potential here, right? Clear? Clear? So VT equals this 1 over 4 pi epsilon 1 into 10 to the power minus 6 over 15 into 10 to the power minus 2 plus the difference delta V. Delta V is 1 over 4 pi epsilon naught 1 into 10 to the power 1 into 10 to the power minus 6 over 5 into 10 to the power minus 2 minus 1 into 10 to the power minus 6 over 10 into 10 to the power minus 2. Clear? Write this carefully. Write this carefully. Consider this as a theory point, okay? Consider this as a theory point because I needed to teach this theory point, but we had a better method, right? This is not a very convenient thing. Why? Think that if you had few shells like this, you find the potential somewhere, then you get the difference, then you add that. Our method was much convenient than this, right? Converting this into a thin shell system and going for answers, it was much better. Okay, but since they have mentioned this in a past paper, we have to know this method too. Okay, clear? Okay, consider this as a theory point. Okay, okay. So put a star and maybe consider it as a theory point and write down things properly. Okay, so got the idea? Got the idea? Clear? As I mentioned, like consider this as a theory point, okay? Consider this as a theory point. So in this past paper, like we had a better method, but for a person who don't know that method, this is the solution, okay? But the problem is assume that you have few shells here, then it's just a lot of trouble, right? You find where you know, then you get the difference, then you add that. You can't write directly values, okay? It's not convenient, right? Okay, okay. So after that, uh, after this, like after that, there are a few other questions again mentioned in the same question. So they have asked us to draw the graph and all. So I'll quickly go through the graph also. Uh, Here you have plus one. Here the internal surface, the external surface, the conductor, how the field intensity would look like, how the field intensity would look like, how the field intensity would look like. So what happens is field intensity goes like this. Then inside the conductor, no field intensity. Then again, it starts from a higher value. Okay, it starts from a higher value. Why? Uh, Here it stops at a larger radius. Again, starts at a smaller radius. See, it stops at a larger radius. Clear? Then again starts at a smaller radius. Smaller distance means higher field intensity. So it goes to zero, then again starts at a higher place, then goes to infinity when you get really close. Clear? In this side, the same pattern. In this side, the same pattern continues. Clear? This is field intensity. Then what about the potential? What about the potential? Potential would look like here you have plus one. Here you have plus one. So the potential would go like this. Like this. Inside that is constant. Inside that is constant. Then again, when it gets close, increases to infinity. Inside the conductor constant, then again reach to infinity. Clear? This is the distribution of field intensity and distribution of potential. Clear? Clear? If you are okay with the question, move to 2005 question, okay? If you have nothing new to learn here, go to 2005 question. And the next thing is, again, they have asked what happens when we put a -1 coulomb into the surface, right? We put an additional charge of -1 coulomb into the surface. Then what happens? When you put an additional charge of -1 coulomb into the surface, nothing new happens. Here you already have +1, -1, then here +1. Then you put an additional -1 here. When you put an additional -1 here, okay? When you put an additional -1 here, this gets cancelled out. That's all. So now you have +1 here, -1 here, nothing at the outside surface of the shell. Clear? Nothing at the outside surface at the shell. Clear? Clear? You have +1, you have -1. Then there was an induced +1. There was an induced +1, but you put another -1 here, which cancels out the overall charge at the surface. Clear? Which cancels out the overall charge at the surface. So there's no resultant charge on the surface. Clear? There's no resultant charge on the surface. So you just have +1 and -1 internally. That's all. You have +1 and -1 internally. 2005 question. 2005 question. Two thousand five, 2005 question. Try 2005 question. You actually can skip if you need the unnecessary parts that you can directly get from the paragraph, okay? Or you only need to teach the static electricity part of the question. So there are some facts asked directly by the paragraph. You can skip them, okay? Okay. So in the question, the initial parts are directly from the paragraph 2005 A-level question. If you are inside a house during a lightning, list two things that you should avoid doing. If you are at outdoors, what is dangerous? Okay. What should you do to protect a building? These are directly from the paragraph, right? These are directly from the paragraph, right? Yes, right. Um, but one part is there which is not related to static electricity, but I'll start there, which is the fourth one. Why do air masses expand and cool as they ascend? This is not related to static electricity, okay? This is not related to static electricity, but I think it's much convenient to like we should learn this part because we did the exact same theory in heat lesson, right? I mean, when a cloud forms, it's just an mass of air, or in any scenario, when they ascend, when they go up, why do they expand and cool down? I'll just give a general answer, okay? I don't know what is mentioned in the paragraph or even whether it's included in the paragraph or not. Why do things expand and cool down when they go up? The pressure decreases, right? The pressure, external pressure, the overall pressure from the surrounding decreases, right? When the overall pressure from the surrounding decreases, it tend to expand, right? Clear? It tend to expand when the overall pressure decreases, clear? And at the same time, it should cool down. Why? If I consider this as an isolated system, okay, I can consider this as a adiabatic process. Delta Q equals delta U plus W. Okay, if heat doesn't provided to the system, if the heat is not extracted from the system, no heat change, which makes me this an adiabatic process. So in an adiabatic process, delta Q is 0, delta U plus W, clear? Then you get delta U equals minus W. Now you see, right? Now, if it expands, okay, if it expands, it's a positive work which makes this part positive. It's a positive work which makes this part positive, clear? Then minus and plus gives you minus, clear? Minus and plus gives you minus, right? Clear? Minus and plus gives you minus, clear? Which makes this what? Which makes this a negative internal energy difference. What is a negative internal energy difference? It is a drop of temperature, right? If the internal energy difference is negative, that means the temperature drops, right? Because the internal energy represents temperature, temperature represents internal energy, right? There's a very strong connection between them, right? Okay. So write this down properly. Write this down properly. It's related to heat lesson. Okay. It's from the heat theory. Properly write this down. Properly write with adiabatic and all. Is it enough time? Yep. Next one. Next one is the actual static electricity part that I needed to teach. Okay. Next one was the actual static electricity part. Using the method of images, show that the magnitude of a resultant electric field intensity E at a point P in figure 1 is given by So they are mentioning something called the method of images here. They are mentioning something called the method of images here. Method of images means something like this. Now, in a cloud, due to a negative charge, maybe due to a negative charge on Earth, positive charge may induce. Positive charge may induce. Clear? Positive charge may induce. Clear? Then the field lines would go like this, right? Field lines would go like this. Field lines would go like this. So it's perpendicular everywhere. It's perpendicular everywhere. Clear? So the field lines would go like this. Clear? Now the problem is it's not easy to find the field intensity, okay? The problem is it's not easy to write the field intensity. Why? It's not easy to write the field intensity. Why? You know how to write the field intensity around a point charge. You know how to write the field intensity between 2 point charges plus q and minus q. You know how to write the field intensity between a plus q and another plus 2q. You know a lot of stuff. You know how to write the field intensity between two parallel plates. We know a lot of things. But do we know how to write the field intensity between a plate and a point charge? Do we know how to write the field intensity between a plate and a point charge? That we don't know, right? We used Gauss theorem to prove a lot of stuff, but none of them provided us the ability to find the field intensity between a point charge and a plate, right? So this is out of our capacity, clear? But they mention something like this to make our life easy. They mention something called the method of images. Method of images means they ask us to assume that if this is minus q and if this distance is x, they ask us to assume that there's a equal and opposite charge at the same distance with the same charge. Clear? Now if we write the field diagram between plus q and minus q, what will we get? What would we get? Like this, then like this, then like this, like this, and like this. Clear? Now see this distribution and this distribution looks almost same, right? Here, this distribution and this distribution looks almost same, right? See, at the exact center, the distribution looks same. So they are telling us that this system is an equivalent system of this one. Clear? They mention us that this system is an equivalent system. They mention us that this system is an equivalent of this system. Clear? That means using this, I can predict this. Sorry, using this, I can predict this. Clear? Because this is out of our capacity. This is out of our capacity. But between 2 point charges, we know how to write the field intensity, right? We know how to write the field intensity. How? Here, what is the field intensity by minus q? It's in this direction. It's in this direction. Field intensity is 1 over 4 pi epsilon q. What is the distance? X over x squared. It is in this direction. Clear? And what about this plus q? Because of that plus q, the field intensity here is also in upward direction, right? So it becomes plus 1 over 4 pi epsilon q over x squared. Clear? So you get 1 over 4 pi epsilon q over x squared into 2, which gives us 1 over 2 pi epsilon q over x squared, which is correct for this system too. So this is an approximation of this system. Clear? This is an approximation of this system. So the reason to choose this question specifically is I have seen them considering this as a theory point now. This is not in the syllabus. Okay, nowhere in the syllabus they teach something called method of images. But since it appeared in 2005, I have seen in some A level papers. Okay, I have seen in some, not A level, in some model papers. Model papers in the sense, in some, I have seen in some like government produced model papers by Kalinga Bandara sir, like yearly model paper produced by government. In these model papers, I have seen them considering this as a theory point. That means they directly give you this question, ask you to find the field intensity here. Something like that is was never mentioned in the syllabus. Okay, there was nothing like that in the syllabus. But since it appeared in 2005, they sometimes consider this as a theory point in model papers. Okay, so it's good to know this. Okay, it's good to know this method. Okay. So after that, now they're asking, okay, find the field intensity in the middle, okay, due to the cloud. So now I know a method. Now in the cloud, now in the cloud, you have a plus q here. You have a minus q here. This distance is h1. This distance is h2. Then this is also h1. With this minus q, I'll put a plus q here. Method of images. Then at a distance of h2, at a distance of h2, for this plus q, I'll put a minus q. Method of images. Clear? Then due to this plus q, field intensity is in this direction. E1. Due to this plus q and minus q, field intensity is in this direction. E1. E1 is equal to 1 over, see now I have the direct equation, 1 over 2 pi epsilon, 1 over 2 pi epsilon, q over h1 squared. And due to this plus q and minus q, you have the field intensity downward. E2. E2 is E2 is 1 over 2 pi epsilon. Charge is q over h2 squared. H2 squared. So now you get overall field intensity E1 minus E2. Why? One field intensity upward, other one is downward. So you get 1 over 2 pi epsilon q over h1 squared minus 1 over 2 pi epsilon q over h2 squared. So you write q over 2 pi epsilon 1 over h1 squared minus 1 over h2 squared. Clear? That's how we get that answer. And it's in upward direction. It's in upward direction. Write this down. After that, after that, uh, after that, they have given us Q, H1 and H2 and asked us to get the answers. That is easy, okay? After they have given us the values of charges, value of H1, value of H2, they have given us everything and asked us to find the answer. So you just substitute the values here and get answers, okay? You just put the values here and get the answers. Then suppose question 6. Question 6. Suppose a single lightning stroke transfers a charge of minus 5 coulomb through a potential difference of 10 to the power 8 volt. 10 to the power 8 volt. Calculate the energy released by this lightning discharge assuming the potential difference remain constant. State two modes of dissipation of energy. So here, if a Q charge goes through a V potential, energy is VQ, okay? If a Q charge goes through a V potential, energy is VQ, clear? Energy is VQ, okay? Energy is VQ. Probably understand it's not half VQ, okay? This is for capacitors. Half VQ is for capacitors. Why? In a capacitor, potential starts at 0. When we give charge only, potential increases to V. So the potential starts from 0 and go to V. Here, it's just a constant potential difference of this and a charge go through that. So it's not half VQ, it's VQ, okay? It's VQ, clear? So the charge is 5 coulombs. Potential is 10 to the power 8 volts. This is the energy. This is the energy. Then 7. During lightning, adults standing on the ground have a higher risk of getting killed even in the absence of a direct lightning strike. State the reason. Yeah. I think even in the paragraph they have mentioned that if you can keep your legs close, feet close to each other, you will have a minimum impact, right? You will have a minimum impact. Why? Current always flows through the smallest path. So if your legs are like this, okay, current would not go through your body up and return down. It will just go like this and go out like this. Clear? Clear? There's no need of going through your body. If your feet is touching each other, current goes through the smallest possible path, okay? Current goes through the easiest path always, clear? It doesn't go through complex paths, okay? Clear? Okay, so, but for a cattle, it's not an option, right? Why? For that animal, legs are always far away, right? Clear? Clear? So if current goes like this, it's not a direct lightning strike. It may strike the ground, but when lightning strikes the ground, it goes to the current, electricity goes to the earth, right? Now here, there's anyways a larger path through this one, right? Clear? There's a larger path through this one. So that means a lot of current going through a long path. And this is not a conductor, okay? A cattle is not a conductor. So it's not a good conductor, it's a non-conductor. Non-conductors resist current a lot. So they produce a lot of heat. So this produces heat. So I mean even animal, people, everyone doesn't die due to current electricity passing through them. It's due to the heat produced by the current electricity, okay? It's the heat produced by the current electricity, okay? Even a perfectly conducting wire creates a small heat, right? When current goes through them, we are not conductors. So we produce a huge heat when current passes through us. Clear? Clear? That is the reason. Okay. Yep. Write that down. Go to 2012 question. 2012. After that, 2000. Yeah, let's first start with 2012 one. 2012 question. Let's go to 2009 first. 2009, then 2012. 2009, then 2012. 2009, then 2012. Okay. Here. Hmm. Ayan. Ayan. 2009 and 2012 question. Please read the question. At least read the question 2009 one. Okay. At least read the 2009 question entirely. Read the interval. Yes. Shall I finish 2009 one first? Yes. It's possible. Okay. Let us numbers images printed by. Okay, it's a printing system. Assume that each spherical droplet emitted from the ink droplets gun has a diameter d, and each droplet produces a circular dot whose diameter is 25% larger than d when it strikes the paper. Find the value d must have for the printer to be able to print 200 dots per centimeter. Okay. So what is the meaning of this? What is the meaning of this? 2009 one, 2009 question. Um, there's a length of there's a length of 1 centimeter here. If the diameter is simple d, there should be 200 dots. There should be 200 dots. That means d into 200 equals 1 centimeter. Then d equals 1 centimeter over 200. But what we need is capital D. So they are telling that D is simple D is 25% larger than capital D. That means capital D into 125 over 100, right? Simple D is 25% larger than capital D. Clear? Clear? So here simple D is 1 over 200 in centimeters. 1 over 200 in centimeters. Here you have capital D and 125 and 100. 125 and 100. So by solving this, we get capital D equals what? Capital D equals 1 over 250. 1 over 250 centimeters. Next, ink droplet gun shoots droplets horizontally toward the paper with a velocity of 20 meters per second. Calculate the vertical displacement of the neutral droplet due to gravity when it hits the paper, which is placed vertically 4 away from ink droplet gun. Shown that this deflection is much smaller than the diameter of the dot printed on the. It's I think 4 centimeters away, right? It can't be 4 meters, right? There's a small printing mistake, but it can't be 4 meters, right? 4 millimeters, right? It's just 4 millimeters away. Clear? 4 millimeters away. Clear? According to the diagram, if this is the paint gun, you can find the paper 4 millimeters away from the gun. So when it goes like this, it will definitely fall down a bit, right? Fall down a bit. Clear? And the velocity is 20 meters per second. Velocity is 20 meters per second. So it will go like this. It will go like this. Clear? It will go like this. So there's a drop like this. Clear? There's a drop like this. Clear? So how can I find that drop? I can apply S equals ut and find the time horizontally, because horizontally there's no acceleration, right? Horizontally there's no acceleration. So distance is 4 millimeters. Distance is 4 millimeters. Velocity is 20 meters per second. So we get what? Here 1 over 5. So you get 0.2 into 10 to the power 3 into 10 to the power 3 seconds. Then to find the drop, let's apply S equals ut plus half at squared downward. Ut plus half at squared downward. Then the drop becomes x. Drop becomes x. Starting downward velocity 0 plus half. Gravitational acceleration is 10. Gravitational acceleration is 10. Time is 0.2 into 10 to the power minus 3 squared, which results in a very small value, right? Which results in a very small value, which gives you 5 into 0.04 into 10 to the power minus 6, which is a very small value. Clear? Which is a very small value even compared to this. Clear? That's what they're asking. Clear? So the gravitational drop should be neglected, I think, in the question, right? Could be neglected. Okay? Could be neglected, because the drop due to the gravitational attraction is very small. Then question B. Each droplet which has to be deflected into a gutter is given a charge of minus 1.5 into 10 to the power minus 10 coulomb by allowing a very narrow beam of electrons from electron gun to strike the droplets under the suitable condition. A potential difference of 50 volt is applied between the parallel plates. If the droplets move across the electron beam as shown in the figure, find the time required for a droplet to pass the electron beam. Okay, so the diameter of a droplet is d and the electron beam is a line. So for it to pass this line, it should move a distance of d and it is moving with a velocity of 20. So it will take a time of d over velocity to pass this beam, right? A beam is a line, so it should pass a distance of diameter to pass the beam, right? Clear? So we get, what is the distance here? Distance here is capital D. Capital D I already know, 1 over 250 centimeters. Capital D 1 over 250 centimeters and divided by the velocity is 20. Velocity is 20. Clear? So you solve this, you get the time. Clear? Clear? Okay. Assuring that all electrons which strike the droplet are uniformly distributed over the surface of the droplet, calculate the electric current due to the emitted electrons from the electron gun during the charging process. Okay. So is it clear up to this point? Is it clear up to this point? Yes? Okay. Now, this is a story. This you have to know current electricity for this. Actually, current means charge over time, right? Rate of change of rate of flow of charge is current. Clear? So this part it's okay if you can't get the answer because it's a bit related to current electricity. You need the definition of current electricity for this. Clear? So it's the charge over time is current. Okay. How fast the charge flows. Clear? So they are telling that a charge of 1.5 into 10 to the power minus 10 coulombs, 1.5 into 10 to the power minus 10 coulombs were provided within this time. Clear? Within this time. Clear? A charge of 1.5 into 10 to the power minus 10 coulombs was provided within this time. So that gives us when I solve this, I would get 10 to the power minus 2 over 20 into 250. I'm not going to do the calculations. This gives us the current in amperes. Clear? This gives us the current in amperes. Clear? Amount of time we got here, amount of charge was given in the text. Clear? Clear? Next. Find the electric field intensity between the parallel plates. They need us to find the electric field intensity between the parallel plates. They are telling that there's a 50-volt voltage difference between the plates. There's a 50-volt voltage difference between the plates. There's a 50-volt voltage difference between the plates. And this gap is it 0.5 millimeters or centimeters? Should be millimeters, right? This gap is 0.5 millimeters, right? This gap is 0.5 millimeters. 0.5 millimeters. So how do we find the field intensity? How do we find the field intensity? Field intensity equals potential gradient. Can you remember potential difference over length? Field intensity equals potential gradient. So potential difference is 50 volt. Gap is 0.5 millimeters. This gives you the field intensity. Clear? Field intensity equals potential gradient. Can you remember? Potential difference over gap. Then, what must be the direction of the electric field? What must be the direction of the electric field? So this is the story. I didn't read the question properly. The target is to deflect this down and put it into a gutter, right? That is the target, right? Deflect this down and put it into a gutter, right? That is the target. So we are providing a minus charge, right? We are providing a minus charge here, right? Clear? According to the question, it's minus 1.5 into 10 to the power minus something coulombs, right? Clear? So for a minus charge, for a plus, field intensity should be in this direction, right? Clear? Why? If the field intensity is in this direction, on a plus charge, force may appear in this direction. On a minus charge, force may appear in this direction, right? So this is what we need, right? This is what we need. Clear? Clear? To push it down, clear? To pull it down, this is what we need, right? So the field intensity is in upward direction. Then, uh, The mass of the charged droplet is given as 4 into 10 to the power minus 11. 4 into 10 to the power minus 11 kilograms. Find the angle theta that the gutter must make with the horizontal direction so that the charge droplet travels straight into the arm. So now the story is this. We can forget gravity for questions, okay? Let's forget gravity for questions, okay? Otherwise, they won't ask that question, right? If we have to consider gravity, they won't ask that question. Now, when it falls into a gutter, it has a certain horizontal velocity and a certain vertical velocity, right? Horizontal velocity is directly 20, right? Initial velocity was 20 meters per second. So it is continuously 20 meters per second, clear? It is continuously 20 meters per second. But what would be the vertical velocity? What would be the vertical velocity? How can I find that? Have to do some calculations, right? Have to do a few calculations. What are the calculations? What are the calculations? The calculations are, okay, the calculations are, uh, uh, I think the length of this was given as 1 millimeter, right? Length of the plate was given as 1 millimeter, right? So this particle is moving with a velocity of 20, clear? So for that particle, it will take a time t, which is length over velocity, which means length is 1 millimeter. Length is 1 millimeter over velocity is 20. Length is 1 millimeter, velocity 20. This gives us the time, okay? This gives us the time 0.05 into 10 to the power minus 3 seconds. 10 to the power minus 3 seconds, clear? Okay. Within that time, this will feel a downward acceleration. How do we get the downward acceleration? Downward force is EQ, field intensity into charge. Clear? EQ, field intensity into charge. What is the field intensity? We got the field intensity. This is the field intensity, right? 50 over 50 over zero point 0.5 into 10 to the power minus 3. This is the field intensity. What was the charge given? It was this, right? 1.5 into 10 to the power minus 10, right? Charge was 1.5 into 10 to the power minus 10. That is the charge. This is the force, clear? Then we know that F equals ma. We know that the F equals ma. Clear? Clear? Okay. Then the acceleration we can get by taking this 50 over 0.5 into 10 to the power minus 3, 1.5 into 10 to the power minus 10, divided by mass. Divided by mass. What is the mass of the particle is given as 4 into 10 to the power minus 11. Clear? Mass is given as 4 into 10 to the power minus 11. Clear? Clear? So what do we get there? What is the acceleration? What is the acceleration we are going to get? The acceleration we are going to get is 50 into 1.5 into 10 to the power minus 10 divided by 0.5 into 10 to the power minus 3 into 4 into 10 to the power minus 11. 51.5, 10.5, 10, 3, 4, 11. Yeah, it's a huge acceleration, right? Did I make any mistake somewhere? Here minus 11, minus 3. Voltage is 50. Voltage difference is 50 volt. Gap is 0.5 into 10 to the power minus 3. Then charge is given as 1.5 into 10 to the power minus 10, right? Is that the charge? Charge given to the droplet? Yes, right? Charge given to the droplet is, yes, it's 1.5 into 10 to the power minus 10. It's correct. 50, yes. zero point 0.5 into 10 to the power minus 3, yes. 4 into 10 to the power minus 11, yes. Yes, I think it's correct. Okay, we are getting a huge acceleration. We will see whether we are getting an unrealistic answer or not. So it's 375 into three zeros. Okay, it's a huge answer. Okay, 375 into and three zeros. So the acceleration is 375 and three zeros. So how can I find the velocity here? Within this time, within this time, okay, it feels this downward acceleration, right? So I can apply V equals U plus AT. So starting downward velocity 0 plus downward acceleration 375 into three zeros, and the time is that. No big issue since the time is also small. Time is this. Clear? Clear? Then what do we get here? We are getting 18.75. Reasonable. 18.75. Clear? So this velocity would be 18.75. Now you can figure out the direction of the gutter, right? Here, here. Okay. The gutter should be directly with the velocity, right? Gutter should align with the velocity, right? So you know the horizontal velocity, which is 20. You know the vertical velocity, which is 18.75. You can find the angle of the resultant, right? You can find the angle of the resultant. This angle of the resultant, clear? In this direction, you have 20. In this direction, you have 18.75. Then you can find this angle, theta. The gutter should have the same angle, theta. The gutter should have the same angle, theta, to receive this. Clear? Clear? Focus this whole part from part B. Yeah. Write down if you missed anything. Nice. Okay. Write down if you missed anything and just mention in the Zoom chat if you wasn't able to write the initial part or anything like that. Okay. Got the idea? And mention in the Zoom chat if you need me to explain any part. Okay. Mention in the Zoom chat if you need me to explain any part. I'll give you the interval. After the interval, I'll discuss 2012 question. After the interval, I'll discuss 2012 question. Time is 11. So I'll start at, yes, 25, 30, 11:30. And I'll just give you a 5 minute interval before starting heat. Okay. So let's start at 11:30. Try to be here by 11:25 at least and start doing the questions. Okay. I'll start the explanation at 11:30. Okay. The time is enough for 2012 one. I'll discuss 2012 one. I'll discuss 2012 question. Two metal plates A and B kept parallel to each other in a vacuum are connected to a voltage source shown in figure 1. A molecular ion of mass m and charge plus q starting from rest from the plate A accelerates toward the metal plate B under the influence of voltage V maintained between the plates. Write down an expression for the kinetic energy gained by the ion when B reaches the plate B. Derive an expression for the velocity V required by the ion when it reaches the plate B. If d naught is the distance between the plates, derive an expression for the time taken by the molecule ion to reach the plate B. Okay, so uh, the story is this. Okay, the story is this. I mean, not a very difficult question, so you can just keep doing the question. Okay, you don't have to listen. If you are okay with the question, keep finishing the question and do another question. Okay, start another question. If you were not able to handle only, then focus here. Okay. Okay. So in this one, okay, in this one there are plates. Okay, there are two plates like this. 2012 one, 2012. There are two plates like this. Potential difference provided is V. Potential difference provided is V. Potential difference provided is V. This is a charge Q. Mass is M. So the question is write an expression for the kinetic energy gained by the ion when it goes to plate B, goes from A to B. So kinetic energy gained, okay, kinetic energy gained is equal to the kinetic energy gained is equal to the okay kinetic energy gained is equal to the potential difference into Q. Clear? Potential difference into Q. Can you remember? When a charge Q goes through a potential difference of V, okay? When a charge Q goes through a potential difference of V, it obtains the energy of V into Q, right? So this is the again kinetic energy, right? This energy, the static electric energy received as a result of going through a potential V turns into the gain kinetic energy, right? It turns into the gain kinetic energy, clear? Then after that, they're asking the velocity, right? So if this is the gain kinetic energy, it is equal to half mu squared. Here I'll get velocity as u. Half mu squared, clear? Then u equals what? U equals square root square root 2VQ over M. Clear? U equals square root 2VQ over M. Clear? 2VQ over M. Then after that, if D naught is the distance between the plate, derive an expression for the time taken by the molecule ion to reach the plate B. So this is D naught. I can find the field intensity. What is field intensity? We know that if we consider the magnitude only, field intensity equals potential gradient. Delta V over delta D. Can you remember? Field intensity equals potential gradient delta V over delta D. Clear? So potential gradient could be written as voltage difference is V. Voltage difference is V. Okay. Voltage difference is V. This gap is D naught. Clear? This gap is D naught. Clear? Gap is D naught. Clear? Voltage difference is V. Gap is D naught. Clear? V over D naught. Clear? V over D naught. Okay. Now you have the field intensity equals V over D naught. Clear? Then then we can find, okay, then we can find the acceleration. How? Acceleration I can get using the force. What is the force? I know that when there's a field intensity E and when there's a charge Q, force will be EQ, right? Force will be EQ. So here I can write EQ. Sorry, E means V over D naught. E means V over D naught into Q. Then again from this side F equals MA. F equals MA, right? So A equals acceleration equals this divided by M. V Q over D naught M. Clear? V Q over D naught M. Clear? V Q over D naught M. This is the acceleration. Clear? This is the acceleration. Okay. Now I have the acceleration. Now I can find the time it takes from here to here, right? Why? Just apply S equals ut plus half a t squared. Distance to be traveled. What is the distance to be traveled? Distance to be traveled is d naught. Clear? Distance to be traveled is d naught. Clear? Distance to be traveled is d naught. Starting velocity 0. We are starting from a velocity 0. Clear? Plus half a t squared. So t equals 2 d naught over a square root. T equals 2 d naught over a square root. Clear? Then I can write here 2 d naught over a. A is this, right? This is a. This is the acceleration. VQ over d naught m. D naught m. So I'll take this part here. I get 2 d naught squared to d naught squared m over VQ to d naught squared m over VQ. Clear? This is the time it takes to go from A plate to B plate. Next, B. Suppose the metal plate B is now replaced with a metal wire mesh so that the write this down, okay, write this down if you need. so that the ions moving through the region AB could enter a field-free region and move towards an ion detector D placed at a distance S from a wire mesh B as shown in the figure. Derive expression for times T1 and T2 taken by ions 1 and 2 to reach the mesh B and indicate which ion reaches the mesh first. Derive an expression for the velocities V1, V2 when they reach the mesh B. Indicate which ion has a higher velocity when they reach B. Derive an expression in terms of T1, T2, V1, V2 for the suitable value for the distances at which the detector D has to be placed so that the detects both ions 1 and 2 in the same time as shown in the figure. Okay. Okay. I'll do all the parts at once. Keep it here. You can write this down. Okay. Okay. So the story is this. Okay. Uh, Here the gap was initially D naught. So I'll quickly go through the question. Gap was initially D naught. Gap was initially D naught. Okay. Okay. You just keep it here. Erase the whole board and start. Write this down if you are not able to write. Okay. Now this field intensity, I know the field intensity. I know why. Potential difference is V. Potential difference is V divided by D naught. Both particles are Q, right? Is that the case? Is it Q1 or Q2 or both Q? Q. Ah. So the force on both particles would be EQ. EQ, which means V over D naught into Q. And at the same time, F equals MA. F equals MA. So the acceleration of both would be VQ over MD naught. I'll take this as A1, okay? I'll take this as A1, clear? This is the acceleration of both particles, clear? So in the first part, they ask the time it takes to reach here and here, right? Clear? And in the second part, they ask what do they ask in the second part? Velocity is v1 and v2, right? Okay. So it's easy. Why? You know the acceleration. So to get the time, s equals ut plus half at squared. Distance is d1. Starting velocity 0 plus half. Acceleration is a1, which is this, okay? t1 squared. So you get the answer as t1 equals 2d1 over a, 2d1 over a1 square root. Put a1 here, okay? Clear? Then what about t2? Again, distance d2. Distance d2 equals 0 plus starting velocity 0 half a1 t2 squared. So t2 equals 2d2 over a1 square root. 2d2 over a1 square root. You have t1 and t2 both now. Clear? Now you have both t1 and t2. Have both t1 and t2. Now you can continue from that. Now we are asking the velocities. Velocities. Again easy. Why? V squared equals u squared plus 2as. Let's use. So starting velocity v1 squared. Starting velocity 0 plus 2. Acceleration a1. Distance d1. So v1 equals square root 2 a1 d1. Similarly, v2 equals square root 2, same acceleration for both, only the distance is d2. And who's higher? Definitely v1 is larger than v2. Why? d1 is larger than d2, right? d1 is larger than d2. So according to the equation, everything else is similar. So v1 is larger than v2, right? Next. Derive an expression in terms of t1, t2, v1, v2 for the suitable value for the distances at which the detector D has to be placed so that it detects both times 1 and 2 at the same time as shown in the figure. Okay. So now we release both at the same time. Okay. So now what happens is D2, this one reach here first. This one reach here later. But this one reach with a higher velocity. So time it takes from here to here would be S over V1, right? Clear? Time it takes for this particle to reach from here to here would be S over V2, right? Okay. I need both to reach here at the same time. Clear? Clear? For that to happen, okay? For that to happen, what should happen is, okay, to guarantee that, what should happen here is, what should happen, or I'll take it here. To guarantee that, what should happen here is, what is the time from here to here? T1. Time from here to here? S over V1. Time from here to here? T2. Time from here to here? S over V2. These facts should be equal. Clear? They should be equal. Clear? Total time should be equal. Clear? Now you just put the values and find S. Okay? What is T1? This is T1. T1 is 2D1 over A1. A1 is this. Okay? Plus S over V1. What is V1? This. Square root 2A1 D1. Here, what is T2? What is T2? This. T2 is this. 2 D2 over A1 plus S over V2. What is V2? V2 is square root 2 A1 D2. What you should do here is put this replace A1 by this and find S. Okay, find S. Clear? So these are actually mechanics questions. Okay, as I always tell, half of the, not half, like 70% of the A level questions are mechanics questions. Okay, 70% of the A level questions are mechanics questions with small other facts here and there. Okay, okay, with small facts here and there. Okay, here field intensity we find from static electricity. Very few path from static electricity. Okay, after that, majority of the question is mechanics question. Okay, okay, that is the nature. Okay, that's the nature. So that's why we always focus on mechanics first, and we have to be really good at mechanics. Even now, if you are having issues with mechanics, okay, if you are not really good at mechanics, work on that. Okay, you have holidays these days, start working on that. Try to improve your mechanics skills. Okay, why? At the end of the day, it, like the result, I mean, there's a huge impact on the result from the ability to understand mechanics questions. Okay, why? Like gravitational, static electricity, magnetics, many questions. Okay, after removing some parts from that lesson, everything else is mechanics. Okay, clear? Here also it's 80% mechanics and 20% static electricity. Previous question we did 80% mechanics and 20% static electricity. Okay, so there are very small part. I'll explain it in 3 minutes and finish. Then let's start it. Okay, the class is until 2, right? Yes. Okay, then no big issue. Really, is it 2 or 2:30? 2. Okay. Who have classes in the evening? Who have classes in the evening? Really? Really? Okay. Okay. Next. Uh, if it quickly finish writing. If you are writing this, quickly finish writing. Quickly finish writing. I'll just draw the diagrams. That's not necessary. Anyone still writing? Anyone? Anyone still writing? Okay, so let's move forward. Uh, Quickly, we were discussing about charged particles, right? And impact from charged particles, right? Throughout the lesson. So, a very small part is remaining in the lesson. That is, how do we give a charge to a system? It's in the last part of your main tute, okay? So, there are different ways. You know that we can, like, when different items get, like, different materials get rubbed, the electrons exchange between them. You had it in all of us, right? Like what happens with silk and ebonite, what happens with polythene and ebonite. Okay, when two particles collide or rubbed, okay, two materials, the material with the loose particles, material with the loose electrons, okay, material with the loose electrons will give electrons to the other guy. Okay, materials with the loose electrons will provide electrons to the other one. Clear? Clear? Materials with the loose electron will give electrons to the other one. Clear? Clear? Um, then it's one method which is not very convenient. Why? You don't know how much charge passes, so it's just a random experiment, not a proper way of giving a charge. Another way of giving a charge is by contact. This initial one works for non-conductors, right? This works for conductors. If you have a certain charge charged conductor, if you have you have a neutral conductor, you touch them, what happens? You touch them, what happens? Huh. This one will give charge to this one until their potentials are equal, right? So this one gets a charge, clear? Another way of giving a charge to object. Again, very not very reliable. Why? Then you can't use this again, right? Then you need someone to charge this one again. Clear? Okay. It's just a one time thing, right? You again have to charge this one then, okay? To return here, okay? So just another method, not that convenient. But there's a good method which is by induction. By induction. There's a good method, it is by induction. By induction, you can charge particles easily. How? See, there's a neutral object. You bring a positive charge close to each this one. What happens? Due to this positive charge, it creates a positive potential on this. Clear? It creates a positive potential on this. Clear? That means this positive charge will attract minus charge towards that and repel positive away. And at the same time, this will give an overall positive charge. Clear? Positive potential to this guy. Now you earth this. What happens when you earth something? Here, to cancel out this potential, when you earth something, its potential should reach to zero, right? Clear? Its potential should reach to zero, right? So to cancel out this positive potential and to make it zero, negative charge will flow. Negative charge will flow towards this front. Clear? Negative charge from Earth will flow towards this guy to make this neutral, to cancel out this positive potential. Clear? We are not touching these two, okay? Now what happens if I remove this positive charge? This additional negative charge will return again. Okay? If I remove this positive charge away, then again this additional negative charge will return. But what I'm going to do is, I'm going to let that negative charge come here and I remove the conductor. I remove the conductor. Now I remove the positive charge. Now these electrons need to go back. But there's no way to go back. So it stays charged. Clear? It stays charged. Okay? So that's how we charge objects. Very small part, official, not in the syllabus, but it's good to know these things. Okay? So yeah, so let's move to the heat lesson. Static electricity is officially over. I'll think and let you know about the plan for the other part. Okay. And I'll let you know